In the past few videos, we looked at some specific features of NMR spectra. Namely, we looked at chemical shifts, that is where a signal shows up on the x-axis as determined by the exact environment that proton is in. We looked at multiplicity, which is determined by how many protons are vicinal to the one being measured. And we looked at integrals, which is the area under the peak as an indicator of how many protons make up that particular signal. Now what we are going to do is further extend our understanding and practice on looking at NMR spectra and concepts related to that by taking organic molecules and predicting what the NMR spectrum of those would look like. And the purpose of this is that we are trying to work up to being able to determine molecular structures from NMR data. And being able to do that requires that we have a really solid foundational understanding of how the structures of molecules relate to their chemical shifts, their multiplicities, and their integrals. So that is what we are going to work on here, is taking a structure and predicting the features of the NMR spectra for those structures that we look at. In order to access the information about the practice problem we'll be looking at here, what you can do is go to the handout of information. And that handout of information that corresponds to chapter 13 will have this practice problem included in it. So let's take a look at this. We'll go through the first one together here, and then I will encourage you for the others to give those a try yourself before you hit play and check your work. So we're asked to provide an expected proton NMR spectrum for each of the following common organic solvents. The following organic molecules show the chemical shifts in the expected range and provide accurate visual representations of the expected multiplicities. All right, so let's take a look at this. So we're going to do the upper left corner problem first. That is the diethyl ether. This compound here, a really common solvent. So in order to evaluate this, I'm going to draw a generic proton NMR x-axis here. I'm going to label my axis as chemical shift. I'm going to include the units, our ppms here. I'm going to start my axis at 0. And then what I'm going to do here is take a look at how many different signals I would expect to show up in the spectrum for diethyl ether, where I would expect those chemical shifts to appear, and what I would expect the multiplicities of those to be. So let's take a look at that. I'm going to redraw my structure of diethyl ether. I'm going to go through this piece by piece. The first piece that I'm going to look at is how many signals we expect to observe for this particular molecule. In other words, how many non-equivalent protons are there in the molecule? That is, protons that are not symmetrical to one another, because symmetrical protons will show up as single signals. So in this molecule, at both terminal ends here and here, we have methyl groups. Those are totally symmetrical to one another. Those are going to show up as a single signal. We take one step into the molecule here versus here, and these two CH2 groups will also show up as their own signal because those are also symmetrical to one another. So we are going to be looking at a proton NMR spectrum here that only has two signals along the x-axis. So somewhere along the x-axis here, we're going to be plotting two signals. We need to think about where those two signals are going to go along this x-axis. In other words, what is the exact ppm that we need to plug them in at? We also need to think about what is the multiplicity going to be of each of those signals. In other words, what's the splitting pattern going to be? So let's think about the splitting pattern next. So for the methyl groups, the multiplicity of those we can calculate using the n+1 rule, where n is the number of vicinal hydrogens. So we pick one of those protons and count how many protons are vicinal to it, how many protons are on the adjacent carbon. So we'll take this proton right here at the right-hand end. We look at the adjacent carbon or carbons and count the number of protons there. Number of protons here on the adjacent carbon is 2. So n+1 is going to be equal to 2 plus 1, which makes 3, which is a triplet. So we expect somewhere on this x-axis for there to be a triplet that refers to those methyl groups. While we're at it, we can think about what the integral would be for this signal. The integral for this signal is equal to the total number of protons that make up the signal, which is going to be 6, because we have those two symmetrical methyl groups that we will expect to see at exactly the same spot along the x-axis. So it's going to integrate to 6. It's going to have an area of 6 and a multiplicity of a triplet. We look at the blue signal next. So that's going to correspond to these two CH2 groups there. The integral of those is equal to the total number of protons that compose those signals. So we have 2 protons here, 2 protons here. So the integral would be 4. It adds up to 4 protons in total. Multiplicity, use the n+1 rule. And to use that n+1 rule, we look at any one of those protons. So I'll take the one right here. Count how many protons are vicinal to it. So we come over to the adjacent carbon and ask how many protons are there next door. There are 3 protons here in this next door position. And so n+1 is going to be equal to 3 is the number of vicinal hydrogens, plus 1 makes 4, meaning that this is a quartet. So now that we have established that our signals in the proton NMR spectrum need to be a quartet that integrates to 4, as well as a triplet that integrates to 6, we need to think about where to plug the triplet and the quartet along this x-axis. And in order to accomplish that, what I recommend is that we take a look at the proton NMR chemical shift table. So let me go ahead and pull that up. So I've dropped in here, at least temporarily, the chart of expected chemical shift values. And you can find this within your packet of information for Chapter 13. I recommend you keep it handy when you're doing the quiz, when you're doing problems related to NMR, etc., etc. So within our structure here of our diethyl ether, we need to think about what we expect in terms of the functional groups. So we have our blue protons that are adjacent to the oxygen atom of an ether group. And in order to predict the expected chemical shift of that set of 4 protons that make up a quartet, we need to look along our expected values here and find an ether functional group and the protons that are directly adjacent to it. So looking along our chart here for the closest thing we can find to an ether, looking around here, looking around, what I see is right here, we have our CH2OR, where remember that we're measuring the chemical shift of the protons that are shown explicitly here. So it's a CH2O group. That's the closest thing I can find, and it's a really good match for the ether group that we have here. And so we expect that ether group to show up in the range of about 3.25 to about 4. So I would accept an answer anywhere between 3.25 and 4 as the location of the signal for that ether group. So I'm going to scribble up top here that we expect the ether CH2 signal to show up at a chemical shift value of about 3.25 to 4. So I'm just scribbling that in with my delta values there because delta is our way of abbreviating chemical shift. So 3.25 to 4 ppm, just to take some notes here to keep myself organized in ultimately drawing out the structure spectrum for this. So our methyl groups, on the other hand, are out at the end here. They're directly bonded to a CH2 group. So looking at the chart here, we don't see anything in the chart that corresponds to an oxygen bonded to a CH2, bonded to a CH3. The closest thing we have here in our chart is over here close to 1 ppm. We have R bonded to a CH3 group. R is defined as an alkyl group. That's not an exact match because we go down the chain a little bit further. We have an oxygen. We know oxygen is electron withdrawing. So that's going to push the methyl group toward kind of the downfield end of this range. So expect the methyl group to show up at around 1 ppm as its delta value, or delta refers to the chemical shift. So I'm going to plug that in as 1 ppm, which is the relatively downfield end range here for a methyl group that's bonded to another carbon, and I'm putting it at the downfield end of that expected range because of the fact that a little bit further down the chain there's this electron withdrawing oxygen that is going to act to de-shield that signal just a little bit. And so now what we can do is go ahead and plug in this information that we have sketched out here in words into our spectrum. And so I'm going to go ahead and move our NMR data information off to the side here so that I can sketch in our NMR spectrum. And for this NMR spectrum, I really only need to show the range of the spectrum that's relevant here. I can cut it off so it doesn't show the full 14 ppm because there would be a lot of blank white space there at the downfield end of that. So I'm going to show up to 4 ppm here. And coming across, I'm going to go ahead here from the most upfield side, going downfield here. We expect that at around 1 ppm, we have the signal for the methyl groups. We expect that to integrate to 6 and for it to show up as a triplet. So I'm going to show a triplet here. Remember, it has that symmetrical peak pattern where that middle peak pokes up above the others. And I'm just going to label that would integrate to 6, meaning the area underneath the peaks here. So the total area that I'm highlighting in gray adds up to 6. And then we come on over to 3.25 to 4 ppm is where we expect to see the quartet for the 2 CH2 groups. So we come on over to 3.25 to 4, and that's going to integrate to 4. So we want to make this area under this peak ideally a bit smaller than that represents 6 protons. And so the total area that I'm highlighting in gray here would equal out to approximately 4. And there's no way for you to draw this out with pen and paper to be exactly an integral of 4 versus 6. But the idea is try to make the total area under this peak a little smaller, ideally, than the total area under this peak, because this represents 4 protons. This represents 6. Our 6 proton signal was a triplet. Our 4 proton signal was a quartet, and we put those at the appropriate chemical shift range of about 3 to 4 ppm for the CH2 group, because those are close to the downfield shifting oxygen, because the oxygen is going to de-shield those protons. And then more upfield, we place the signal for our 2 methyl groups that integrates to 6 hydrogens as a triplet here, because that is going to be shielded by the fact that there's an alkyl group directly bonded there. So this is the idea of drawing out a representative expected proton NMR spectrum for common organic molecules. And you should be comfortable with doing this sort of thing on the upcoming quiz. There is more practice for this when you look at the worksheet for chapter 13. And I strongly encourage you to go ahead and keep playing this video to go through the NMR spectra for the remaining 3 examples. I would suggest that you hit pause between each one and try to work it out on your own, and then use the video as a way of checking your work to make sure that you are learning the material and mastering this so that you're ready to rock and roll on that upcoming quiz. So let's take a look at the next example. So let's take a look at the upper right-hand corner structure. This is ethyl acetate. It's a common component in nail polish. It's commonly used as an organic solvent for extracting organic compounds. And thinking first about how many signals we would expect to see in the proton NMR spectrum for this molecule, we need to pick out how many non-equivalent protons we have here. So we have a set of equivalent protons. Here's that CH3 group. Nothing else in the molecule is symmetrical to that. So we come over to here, and that's going to be its own set as a CH2 group in pink. We come on further, and we have, which I'm going to show in blue, another set of protons there as our CH3 group at the end. So we expect the proton NMR spectrum for this molecule to have a grand total of 3 signals. What are the multiplicities, integrals, and chemical shifts of those 3 signals going to be? So we start off here at the right-hand end of the molecule with our CH3 group. The integral of that, I'm going to sketch in as 3 hydrogens, because that's a CH3 group. Multiplicity, use the n+1 rule. So n plus 1 here, number of vicinal hydrogens plus 1. There are 2 vicinal hydrogens because there's this adjacent carbon here that has 2 hydrogens. So 2 plus 1 makes 3. So that's going to be a triplet. Looking at, and I'll slide back in here, our NMR data information. So looking at the empirical values of NMR data, what we can see here, taking a glance at this, the closest match that we have for this, since we have a CH3 group bonded to a CH2 group, the best match is going to be that we have this group right here that's a CH3 bonded to an R group, where R is defined as an alkyl group. That's going to be the best fit we have for this. So we're going to expect the chemical shift here at the end to show up around 1. It's going to be toward the downfield end of that pink highlighted range here, since it is just a couple spots over from the electron withdrawing oxygen atom. So I'm going to plug in the expected chemical shift as approximately 1 ppm. Then we'll go over to the next proton in line and do the same exercise here. So here at this position, we have a CH2 group. So its integral is going to be 2. The multiplicity, applying the n+1 rule, is going to be equal to 3 plus 1, meaning 4 total. So it's going to be a quartet. And we say it's a quartet because we look at the number of vicinal hydrogens. There's 3 vicinal hydrogens. 3 plus 1 makes 4, so it's a quartet. And then our chemical shift, we take a look at our chart of values that we will always have access to. And in that chart, we are looking for a carbon that is adjacent to an oxygen. Ideally, that could be a carbon that's adjacent to an oxygen and then has a carbonyl there, like an ester group, as we're seeing here. But we'll see if we have anything that matches up well with that, having an ester group. So looking through our chart here, the best match I see within this chart is that if we take a look right here, we have the scenario where we have a carbonyl directly bonded to an oxygen, and that oxygen is directly bonded to a CH2 group, where the R groups are the alkyl groups. So this group right here that I'm circling at the bottom, kind of middle of the NMR chart, is your best match. It is the best fit there, and it's actually a really great fit because it's a CH2 group directly bonded to an oxygen, directly bonded to a carbonyl with alkyl groups flanking on both sides, so it's perfect for this. And that range is between about 4.2-ish and approximately 5. So I'm going to say, just to hit the middle of that region, we're going to predict that the chemical shift of this is around 4.5 ppm. This doesn't have to be exact if you're asked to draw this out on a quiz, but it does need to be somewhere within that expected range. So make sure you hit it somewhere within that 4 to 5 approximate range there. So 4.5 ppm is what we're going to plug that in as. Then last but not least, we come over here to our left-hand terminal of the molecule in blue. We have a CH3 group. So since it's a CH3 group, the integral is going to be 3 hydrogens. Multiplicity, use that n+1 rule. N in this case is equal to 0, so the multiplicity is 0 plus 1, which is a singlet. There are 0 vicinal hydrogens because we look at this adjacent carbon as a carbonyl. There's no hydrogens directly bonded there, so we're going to have a singlet. And then finally, last but not least, looking at the chemical shift that is expected there, I'm going to plug in my approximate value, so that little tilde symbol. And we will go ahead and look for a carbon with some hydrogens that is adjacent to a carbonyl, and ideally also further adjacent to the oxygen atom here. So ideally, we're looking for an ester group where we're looking at the carbon that's directly bonded to the carbonyl. If we can't find an ester, we'll go with like a ketone or some other carbonyl containing group where we're looking at the carbon adjacent to the carbonyl. So scrolling through here, what do we find that will work for this? So in our ester groups, we have an ester group right here. That's not going to work because our carb CH2 group is directly bonded to the oxygen, not directly bonded to the carbonyl, so don't try to use this one. Going through here, we have a ketone. That's somewhat of a match here. So we have the carbon and hydrogens there that are directly bonded to the carbonyl, so this might work. An even better match would be this one up here because we have a carbonyl directly bonded to a methyl group. So that's going to be a better match here because that's a methyl group directly bonded to the carbonyl rather than a CH2 group directly bonded to the carbonyl. So right here, we're in pretty good shape. Looking along, this is not going to match very well because that's an oxygen rather than a carbonyl directly bonded to the CH3. So I think our best fit, looking through the available information here, is going to correspond to this group right here. So we're seeing that showing up between about 2 and 2.5 or so. I would expect for our particular case for this group in blue to show up at the downfield end of that range because it has an extra electron withdrawing group nearby. So we have the carbonyl group, which we see here in our schematic. And then this R group is not just an alkyl group. It has that oxygen there. Oxygen is electron withdrawing due to its electronegativity. So that's going to pull this signal toward the downfield end of that range. So I'm going to plug this signal in at something like 2.5 ppm to emphasize it's at the downfield end of that range due to the fact that We don't just have a carbonyl there bonded to an alkyl group. We have a carbonyl bonded to an oxygen, which is going to move the signal a bit downfield. So now that we have this information laid out, let's plug this into the NMR spectrum. So I'm going to scoot our NMR chart out of the way. I'm going to draw in my x-axis, starting at 0 ppms, labeling my axis as the chemical shift. Units are ppms here, and the x-axis span needs to run from 0 to our most downfield signal. Most downfield signal is at about 4.5, so I'm going to go ahead and terminate this at 5 ppm. So I'm going to sketch out 1, 2, 3, 4 as evenly as possible across that axis. And then I'm going to go ahead and sketch out this spectrum. So the most upfield signal is going to be that methyl group in green on the right-hand end of this structure at 1 ppm. So I'm going to come on over to 1 ppm, and I'm going to draw a triplet that hopefully integrates to 3, has an area underneath it of 3. So we'll go ahead and do that. So that's our triplet at 1 ppm. Coming on down here, downfield to 2.5 ppm, that gets our methyl group that's at the far left-hand side of the molecule that we're going to put at about 2.5, and we're going to show that as a singlet. That should also integrate to 3, so the total area under this signal should be equal to the area under those other 3 signals put together. So what I'm trying to envision here and sketch out as best I can, definitely not perfectly, but as best I can, that the area under this signal at 2.5 in gray is equal to the total area of all of this gray material that I'm making at 1 ppm. And then going toward our most downfield signal is at about 4.5 pm. That corresponds to the protons in red that were the CH2 group. So I'm coming on down to 4.5. That's going to be a quartet. So I plug those in as a quartet, and I aim for that signal to be smaller in terms of area than the others because of the fact that it integrates to only 2 protons instead of 3 like the other signals. So if we want to label the integrals on here, we could label this as 2H, this is 3H, and this is 3H to indicate those integrals as well. So that's going to be our expected proton NMR spectrum for this ethyl acetate molecule. Let's do the next example. So we go onward to the third example here, which is our structure of methanol in the lower left-hand corner. And in the structure of methanol, we are going to expect to see a signal for the proton here that is part of the hydroxy group, and then one other signal corresponding to our methyl group. So our protons here are going to show up as a single signal as well. So let's take a look at what the expected multiplicities of those chemical shift and integral would be. So for our lone proton that is connected to the oxygen, we're going to expect that the integral of that is going to be 1 because it's just one proton there. The multiplicity is going to be a singlet. And one thing that you can keep in mind as a general rule is that hydroxy group protons and protons bonded to nitrogen generally show up as singlets because this oxygen, or if there were nitrogen there, we could think of it this way too, is going to essentially block any multiplicity further down the chain. So protons that are connected to heteroatoms, meaning protons connected to oxygen or nitrogen, generally show up as singlets. So that is something to keep in mind there. And then the chemical shift of this will vary wildly. As we look at our chart here, the chemical shift of an alcohol ranges from about 1 to about 6 ppms. So we can put that anywhere in that range. I'm just going to plug it in at about 3 ppm to hit right there in the middle of that range. But in actuality, it could be, depending upon the exact environment that the NMR spectrum is collected in and what type of hydrogen bonding and the extent of hydrogen bonding going on, it can be anywhere in that range there. So then next up, we come over to the methyl group. Methyl group, looking at the integral, going to be 3. Multiplicity is going to be a singlet because, again, we don't have any vicinal hydrogens. Vicinal means that it's attached to an adjacent carbon. There are no adjacent carbons. There's an oxygen instead, so that's going to cause this to be a singlet. And then the chemical shift that we'll plug in here, looking for CH3 that's directly bonded to an oxygen. Taking a glance through this, CH3 that's directly bonded to an oxygen. We have an alcohol group here. That's a pretty good match. It's a CH2 rather than a CH3, but that might be the best we can come up with here unless we see a CH3OH. We have to find the best fit here. Looking through this, I don't see any CH3OH specified explicitly, so we're going to go with this CH2OH here, which is somewhere in the range of about 3 to 4 ppm. So I'm going to say that we'll plug this chemical shift in at about 3.5 ppm. So what we'll do now is I'll just shrink this down a bit so that we can take a look at the proton NMR spectrum and sketch that out here. So our proton NMR spectrum, I'll go ahead and put in the upper right-hand corner here where our x-axis has our chemical shift in ppms. Chemical shift range I'm going to show from 0 to 4 ppm. So I'm going to plug in 1, 2, 3, and 4. And looking at our signals that we expect to show up here, we anticipate that we will have two signals, one for the hydroxyproton and one for the methyl group. So coming along the x-axis here at 3 ppm, we need to plug in a singlet that integrates to 1. And then coming along the chain here at 3.5, we have a 3 proton signal that is a singlet as well. So I'm going to try to make that 3 times larger than the other one, like so. And so this is going to correspond to our 3 protons that make up the CH3 group, our 1 proton that makes up the hydroxy group proton, to give us the expected NMR spectrum of methanol. So let's take a look at our final problem, last but not least. We have acetone, this 3-carbon ketone in the lower right-hand corner. Now in this 3-carbon ketone, there are 2 methyl groups that I'm highlighting green. Those methyl groups are equivalent to one another because they're totally symmetrical to one another in the molecule, and therefore those are going to show up as one signal that integrates to 6. They're going to show up with a multiplicity of a singlet because of the fact that they have no vicinal hydrogens. If we look at this carbon and the hydrogens there, we look at the adjacent carbon, there are no protons there, so therefore this is a singlet. And then as far as the chemical shift goes, predicting where the chemical shift is at along that ppm range. So along the ppm range for the chemical shift, we have a CH3 group that's adjacent to a carbonyl. So looking at our chart here and thinking about what we can do with that, where we can go with that, we have in our chart looking for a ketone. We have R bonded to a carbonyl, bonded to a CH3 that I'm circling there. That's about 2 to 2.5. That's going to be a great match. So we want to put that signal between 2 and 2.5 ppm. So our chemical shift value going to be at about 2 to 2.5 ppm. So we'll go ahead and sketch this out. On our x-axis, I'm going to show that from 0 to 3 ppm with our chemical shift in units of ppms. Put 1 and 2 on the x-axis, and at about 2 ppm, that's where we want to show our singlet signal. And we'll go ahead and plug that in, and that will be the entirety of the NMR spectrum for acetone. So out of this video, you should have gained additional confidence and ability to predict how the structures of organic molecules relate to their chemical shift, multiplicity, and integral in an NMR spectrum. In the upcoming videos, what we are going to do is work in the opposite direction. We are going to start with NMR data, possibly in combination with IR mass spectrometry data, and work toward determining the complete chemical structures of organic molecules, applying this information much like solving puzzles.